beginning of this course there were more people. My eyesight's getting steadily worse, but I'm pretty sure that there were 5 or 6 people and steadily the numbers are dwindling. We're down to 2. The question is there going to be anyone left by the end? All right. So, today I'm going to quickly finish up a little bit about the Feynman propagator, and then we're going to get on to the Dirac equation. So, all right. So, perhaps I just say a little bit about the history here, which will maybe, to explain the terminology, why it's called a propagator. So, Feynman in the 1940s. So, at that time, many people thought quantum field theory was unworkable. Unworkable, inconsistent, largely because of the infinities that plague the theory. You try to calculate anything that you're interested in, and tend to come out to be infinite. People didn't know how to handle this. So Feynman, in the 1940s, he built up an intuitive method, intuitive pictorial method without quantum field theory. So what he did, he would imagine that things like this, he would imagine paths in space-time, each with an amplitude, and you would sum over possible paths, you would add amplitudes. So for instance, he would imagine, let's say you had an electron and a positron, and they are scattering off each other. He would imagine that he would associate trajectories, and he would imagine that there would be a photon that would be exchanged between here. Imagine one of the particles emits a photon that's absorbed by the other one. And you could also, for instance, if you're interested in the probability that an electron, let's just say that 2 electrons, just to keep this, let's say 2 electrons are scattering. You can say, well, there are different possible processes that can contribute to this. One is that the electrons just exchange a single photon. So there's some amplitude for this process. Let's call it A1. But it's also possible, so here there would be some initial momenta, and here there would be some final momenta. But it's also possible that the electrons could exchange 2 photons. And giving the same final momenta. So you have plus, there are all kinds of other possibilities. And what you would do is you would say, well, the amplitude for this process is equal to A1 plus A2 plus blah, blah, blah. And then the probability is just given by the modulus squared of the amplitude. Now what Feynman did, he invented rules called Feynman rules. Feynman rules, which are basically, they are a list of rules for the amplitudes. A1, A2, etc. So there are rules you can write down, which we'll come to. They're things like, well, these rules involve the Feynman propagator. The Feynman propagator. So for example, in this diagram here, there is a contribution from the photon propagator, which is proportional to 1 over k squared, where k is the momentum of the photon. So here then there's a momentum associated with this photon, and each of these vertices, the momentum is conserved, so this k is the difference between P1 and P1 prime. Now you will remember we were looking last time at the Feynman propagator for the free Klein-Gordon field. And we saw that the Feynman propagator in momentum space looked like this: 1 over k squared minus m squared. This was for the Klein-Gordon field, for the massive Klein-Gordon field. Now, if you put n equal to 0, you see, so for the case of the electromagnetic field, the mass is 0. So this here, this is just the Feynman propagator for the electromagnetic field. And it appears in these rules. Basically, the amplitude for this thing is proportional to 1 over k squared. There are also other factors that involve the electrons, and we'll come to that. So what Feynman did, he cooked up a list of rules. He said, well, given any one of these diagrams, here are the rules for when you have a photon line, you associate a factor equal to this, and blah, blah, blah. And he built up these rules. And the whole thing worked very well. And you can, given any process, if you say, well, let's imagine 2 electrons scattering it off each other, what you can just draw in pictures. You can see, well, the kinds of processes that could contribute, and then you could use these rules to calculate the amplitude. You square the amplitude, you get the probability. And this was done in famous paper published, the sort of definitive paper published in 1949. So now, what happened then is that afterwards, soon afterwards, people realized that, well, actually, if we're careful, quantum field theory, done carefully, actually implies the Feynman rules. Feynman had managed to cook these up before people derived them from quantum field theory. But what you can do in quantum field theory, if you have, for instance, the Dirac field interacting the electromagnetic field. And then what you do is you develop a perturbation series. Perturbation series that we will come to later on. You can ask what will happen if I have, for instance, an initial state where I have, let me just draw it like this. I can imagine here is an electron with momentum P1, an electron with momentum P2, and I can ask what is the probability of making a transition to a final state where I again have two electrons but with two different momenta. You can work this out in the interaction picture. The interaction picture will involve an interaction Hamiltonian that appears here. This is the interaction between these two fields. When you develop this perturbation series, you find that each term in the series can be represented by a diagram like this. There is a mathematical correspondence between the terms in the series and these diagrams. So the sort of standard viewpoint, from the point of view of quantum field theory, we would say, look, there isn't real physics to these diagrams in the sense, that you shouldn't think of the photon being exchanged, these lines. What these diagrams really are a pictorial representation of terms in the perturbation series. They're very handy, they're a nice way of summarizing the results, but from the point of view of quantum field theory, this is what is going on. You have a perturbation series describing the interaction of these fields, and it's sort of what we'll come to, and I'll sketch how this works. It sort of involves some tedious and not very intuitive algebra, the way you develop this series, but you can show that each series corresponds term by term to these kinds of diagrams. So the diagrams are useful. What we'll do, once we show that the series of terms corresponds to these diagrams, in practice, once you derive the final rules for these diagrams, what you do in practice is when you want to, let's say you want to calculate the probability for a certain process, electron-positron annihilation, you don't work out the perturbation series. What you do is you just draw the Feynman diagrams because it's quicker, it's clear, and we know they give the right answers. But ultimately, from the point of view of quantum field theory, the basis of this comes from the perturbation series. And we'll see that when you develop the perturbation series, the terms in the series contain the Feynman propagator. The Feynman propagator keeps coming up. Okay, and we'll see how that comes up. So, to remind you of how the Feynman propagator is defined, I'm going to give you a quick, so we went over this in some detail on Tuesday, but really everything you need to know about the Feynman propagator can be summarized in three things. So one is the definition of the time-ordered product. So, make sure I get this right. So, taking the simple example of the scalar field, the time-ordered product, let me maybe make some room. So just three things you really need to know from last time. So the definition of the time-ordered product, that this is equal to, so I have a product of field operators at two different points in space-time. So if t is bigger than t prime, if t prime is bigger than t. So I have a product of field operators at points x and x primed in space-time. The time-ordered product says, well, you leave them in the same order if t is bigger than t prime, and you reverse the order if t prime is bigger than t. So in other words, the order should be so that time is increasing from right to left. Okay, time is increasing. It's just a mathematical definition, what we mean by the time-ordered product. So that's one thing you need to know. The second thing you need to know is the definition of the Feynman propagator. So the Feynman propagator is defined to be the vacuum expectation value. In other words, the average value in the vacuum state of the time-ordered product. And we'll see when we develop the perturbation series, in the interaction picture, you get a series of terms in the perturbation series. The time-ordered product will naturally come up, and these functions will appear. We'll see this later on. So that's the definition of the Feynman propagator. And then finally, number 3, the third thing you need to know about the Feynman propagator, which we didn't quite get to last time, is that it can be expressed by the following integral. Feynman propagator can be written as 1 over 2 pi to the 4th integral d4k e to the minus I k dot x divided by k squared minus m squared plus I epsilon. Note here, we have integral d3k as usual, integral dk0. Was I using uppercase or lowercase 0? Is going from minus infinity to infinity. The whole real axis. There's nothing in the complex plane here. Okay, K0 is not going in the complex plane. It's just being integrated along the whole real axis. And epsilon is positive, but going to 0. So it's infinite, it's arbitrarily small, but positive. And if you look at this, you know, this is a four-dimensional Fourier transform, and so we say that, well, the Feynman propagator in momentum space is equal. You look at this, well, as a four-dimensional Fourier transform. The Feynman propagator in momentum space is 1 over k squared minus m squared plus I epsilon. Often you can just leave off the I epsilon because epsilon is going to 0. But so everything you really need to know about the Feynman propagator is on this blackboard. So all the stuff we went through on Tuesday was just, you know, instead of just pulling this stuff out of the hat, sort of show you where this comes from and all that. But everything you need to know really for the purposes of this course is here on this blackboard. So now let me just connect this, this last expression where we were last time. Last time we had an expression for the Feynman propagator as a contour integral with k0 taking on complex values. So where does this come from? All right, so where we were last time, we had derived, and I'm sure you've been checking this in your evenings, Tuesday evening, Wednesday evening, you went through all the steps, you checked this. We had the following expression. We had an integral like this, d4k e to the minus I k dot x over k squared minus m squared, where k0 was going into the complex plane, and here we have 2 points, we have poles. Here is where k0 is plus omega, k0 is minus omega, remembering that k squared minus m squared is equal to k0 squared minus omega squared. So there are poles when k0 is plus or minus omega. And this contour, the Feynman contour, goes like this. It goes below, then goes, this is supposed to be going along the real line. This is going along the real line, it dips below this contour, goes along the real line, above this contour. And you have to complete the contour depending on what the sign of time t is positive. You complete the contour down here, and the contribution as this semicircle, remember this of course line is extending out to infinity, this semicircle is extending out to infinity. The contribution to the contour integral from this part actually goes to 0 as the radius of the circle goes to infinity, because it's damped. If time is positive and you have the circle down here, there's a factor here that goes e to the minus infinity, so there's actually no contribution from it. So it's just a contribution really from the integral along this line here. Anyway, that was the expression we had. So then where does this come from? Where does this come from? So what happened here is there's a little trick. Some people call it, so Feynman invented all kinds of tricks. So Feynman's, I think I've seen this referred to sometimes as his I epsilon trick. Feynman was good at tricks, including cracking safes and all kinds of things. But anyway, the I epsilon trick is to say, well, what we can do, look, it's a bit complicated, we worry about deforming this contour. Why don't we instead just move the poles slightly? So what we can do is we can say, well, this should be equivalent to the following. Let's take, again, we've got the real part, k0, imaginary part of k0. But what we're going to do is we're going to move the poles. We're going to move that pole up a little bit, and we're going to move this pole up a little bit, move this pole down a little bit, and just integrate along here. So we're just going to do the integral along the real axis, as I mentioned here. We just integrate k0 along the real axis. Now, how can we move the poles? Well, what you can do is go over here. Is you can, excuse me, begin with this expression. So here's the expression we have with the contour integral. And what we can do, let's just first of all just rewrite this in terms of k0 squared minus omega squared. All right, this is the definition we have of the Feynman propagator in terms of the contour integral. And what we can do now is, let's replace this. Replace it with something slightly different. Is we're going to say, well, let's write this as just an ordinary integral with the k's going from along the real axis. Oops. And let's replace this term here by the following. We're going to write, so I need to write k0 squared minus omega squared. So we can write this, so we'll change it as follows. We'll replace omega squared by omega minus I eta squared. Okay, so we're replacing omega squared by omega minus I eta squared. So what does that mean now? Is that this pole here is at k0 equals minus omega minus I eta, and this pole here is at k0 equals plus omega minus I eta. So in other words, if we're having poles at minus omega and plus omega, I've got plus or minus omega minus I eta. So there's just this, we've got I eta just been shifted slightly along the imaginary axis by eta. Right? You just shifted the pole slightly. And if you look at this, if you expand, so omega k0 squared minus omega minus I eta squared is equal to k0 squared minus omega squared plus 2I eta omega plus eta squared. Let's ignore the eta squared because this eta is going to 0 anyway. Remember, eta is going to 0. Right, we just need eta can, oh sorry, I don't think I mentioned that, but eta can be very small. Remember, I just have to skirt below the pole if I can come arbitrarily close to it. So I only need to shift. If I'm going to integrate along the real line, I only need to shift the pole up by an arbitrarily small amount. So eta is very small. So if you now look at this, if I take epsilon is equal to 2 eta omega, okay, then this term here is just I epsilon. And you see I have now this term here, I recover, basically I get this with 1 over, I will have k0 squared minus omega squared, k0 squared minus omega squared plus I epsilon, which is just 1 over k squared minus m squared plus I epsilon. In other words, it's the same as this integral. So what I'm saying is that the expression we had for the Feynman propagator as this contour integral can be written more straightforwardly like this, as just an ordinary integral over the real axis for k0, but just in the denominator here putting in an I epsilon, where epsilon is positive and arbitrarily small. Okay, so what's going to happen? What's going to be, when it comes to the Feynman rules, what you're going to need to know is this here. Because when we, usually in calculations, you're interested in, well, I've got certain incident particles with certain momenta, particles coming out with other momenta. The amplitudes for these processes in involve the Feynman propagator in momentum space. In other words, this here. If you want to calculate, for instance, electron-electron scattering, you'll need to know the photon propagator, which actually looks just like this. The only difference is for the photon propagator, there is a term G alpha beta in front, which is just the space-time metric. G alpha beta, we'll come to that. But apart from that, the form is exactly like this. Okay, so that's enough about the Feynman propagator. We can move on to the Dirac equation, but just first in case, are there any questions? Questions?
So what are these amplitudes?
Sorry?
I guess what are these amplitudes, and then what you said the probability is the sum?
Yeah, right. So the amplitudes, so they're often called probability amplitudes. They appear in quantum mechanics, but to actually get the physical probability, you have to take the modulus squared of the amplitude.
It seems like these are for different events. So if you have two electrons that exchange one photon, two if they exchange two, but you're summing the amplitudes.
Right.
To find the probability of the single.
Well, exactly. So what happens is, so here we're touching on peculiarities of quantum mechanics. So is normally, so in classical, what you might call classical probability theory, you would say that the probability for an event is the sum. Probably, there are different ways in which this event can occur. You would sum the probabilities. Whereas what happens in quantum mechanics is you have an amplitude for an event, which is a sum of amplitude. The event can occur in different ways. You add, these amplitudes are complex numbers. And then the probability for the event is equal to the modulus of this squared, which you could expand this out as a1 squared plus a2 squared plus interference terms. So, this is the standard view. So, I mean, the classic example is like the two-slit experiment. I fire an electron at the screen, and I ask what is the probability to land at X. So, there are two ways in which it can happen. So, then there's a probability amplitude to go through one hole. There's an amplitude to go through the other hole. The total amplitude is the sum of the two, and the probability is the modulus squared, which is not the sum of the probabilities for each hole. It's the sum of those probabilities plus an interference term. So it's this kind of thing.
When you exchange a single photon versus exchanging two, you're saying these are the same event.
So just as, so let's say we have, let's say what you're interested in is, let's say you're interested in this event, let's call it E. The two electrons scatter off each other. They've got the initial momentum P1, P2, and the final momentum P1 prime, P2 prime. This event can occur in the Feynman diagram picture. It could occur in many different ways, but let's say one way in which it could occur is by the exchange of, let me just write 1, 2, 1 prime, 2 prime, by the exchange of one photon. Another way in which it could occur is by the exchange of two photons. Plus, there are other ways, it could be 3 photons, it could be many. Now, this is the standard way of thinking about this, is saying this is a bit like the two-slit experiment. You say, how did, I fire an electron at the screen and it lands here, how did it get there? Well, there are two ways it could have got there. It could have gone through this hole, or it could have gone through this hole. In quantum mechanics, somehow it goes through both holes and neither, and there's all this woolly talk, which is all baloney, to be honest with you. You can quote me on that on camera. It's all load of baloney. But teaching you the standard viewpoint says, well, you can't say that it went through one hole or the other. That's meaningless unless you actually measure which hole it went through. If you don't measure which hole it went through, you can't say that it went through one or the other. You have to add a contribution from each. But the way the contributions add, it's not the total probability is not the sum of probabilities for this plus the probability for that. It's the sum of amplitude squared, which gives you this is equal to mod phi 1 squared plus mod phi 2 squared plus interference terms. So that's why you get the wavy pattern here. Now it's the same kind of idea here. Feynman would say this event can occur in many different ways. For example, two alternatives are it could exchange one photon or it could exchange two. If I don't, I'm not measuring the photon exchange. All I'm measuring is the initial and final momentum of the electrons. That's all I'm interested in. So I've got some incoming state, I fire in two electrons, and then I measure the momentum of the electrons when they come back out. In this picture, you say, well, it could have occurred this way, it could have occurred this way, and I have to sum the amplitudes. I don't know which process occurred. In fact, the standard view would be you can't say one or the other occurred, just as you can't say the electron went through one hole or the other. In some sense, both occurred or both contributed. So it's the same idea. The probability, I have to take the modulus squared of this amplitude, of this total amplitude. So there's a funny visit, you would say that, well, what happens here, there are various contributions from different processes. And if you say, well, which process occurred? Was it this one or was it this one? It's like asking here, well, which hole did the electron go through? The usual view is, well, if you didn't measure which hole it's going through, it went through both and neither. So, is that...
Yeah, but does this also correspond to our understanding that the photon is just this excitation in the field?
Okay, well look, all right. So look, from the point of view of quantum field theory, all of this is just symbolism. This idea of that there's a photon being exchanged. There's no, there are two kinds of fields. There's the Dirac field, there is the electromagnetic field, and they have very different energy levels, different modes can be excited. And I'm starting up with an incoming state where two of the electron modes are excited, and I have a final state where two electron modes are excited. And if I ask, well, what is the probability of making a transition from this to this? You develop the perturbation series and you get a series of terms that mathematically are the same as what you get from the Feynman rules. But from the point of view of quantum field theory, there's no such thing as photon exchange. There's no such thing even of particle trajectories or what we call particles, just energy levels of field excitations. So, so from the point of view of quantum field theory, all this stuff is just some sort of convenient mathematical shorthand. Instead of writing down these complicated terms of the perturbation series, there is basically, you would say there is a correspondence between if you write down all the topologically possible Feynman diagrams that correspond to a certain process, there's a mathematical theorem that tells you that corresponds correctly to the perturbation series. but you shouldn't think of these as physical. That's quantum field theory point of view. Feynman did think of these as physical. He did think of these processes as occurring, but with this funny probability calculus where you add amplitudes and then get the probability at the end by squaring the total amplitude. That was Feynman's view. Basically, this view was actually very, very fashionable in the 40s, 50s, 60s. There were people who thought that quantum field theory was just ill-defined, and that really the physics was in the Feynman rules. But there was something of a renaissance of quantum field theory in the 70s, where people found ways to describe even the strong interaction with quantum field theory. A lot of progress was made. And nowadays, let's say the mainstream view is that quantum field theory is the theory. These diagrams are just a symbolic representation of a perturbation series and nothing more. That's the view. So anyway, that was a long answer, but anyway, maybe it's something worth knowing. I mean, the diagrams are very useful. As I said, towards the end of this course, once we derive the Feynman rules, then when you actually want to calculate anything, you just use the Feynman rules. The perturbation theory, all this, in a sense, so if you're a particle physicist working at CERN, you want to calculate the probability of cross sections of all these various processes, you just use the Feynman rules. No one sits down and writes down the quantum field theory and develops the perturbation theory. Nobody does that. So there's a sense in which Feynman is still right, in a practical sense. Anyway, let me get on and introduce the Dirac equation, because spring break is coming up, and most students are going to be lounging around on the beach, soaking up the sunshine, drinking margaritas, whereas you're not going to be wasting your time with all that. You are going to be learning to love the Dirac equation. Fantastic. Okay, so all right, so the Dirac equation, I mentioned at the beginning of this course that there's a lot of historical confusion. Dirac thought he was finding a relativistic version of the Schrödinger equation. There's no such thing. From the point of view of quantum field theory, what we're going to describe here is there is something called the classical Dirac field. So think of this as, well, there's the electromagnetic field, there's maybe a Klein-Gordon field, if there are scalar fields in nature that describes a Higgs boson. And there's something called the Dirac field. And once you have these fields, once you have a classical description of these fields, you can quantize them by promoting the fields to operators. We're going to come to that. What we're doing at first is just looking at the classical Dirac field. So the classical Dirac field is a four-component complex field. So we'll write it like this. We have four components: psi 1, psi 2, psi 3, psi 4. These components are complex. Psi 1, psi 2, psi 3, psi 5 have real and imaginary parts. Just think of it, here we have a column vector with four components, a four-dimensional column vector. We often write the components, we can write the components as just psi, we're going to use an index alpha, where alpha goes from 1 to 4. So beware, alpha is, so this is often called, the four-component complex field, the Dirac field, is often called a spinor field. It is a field that contains intrinsic angular momentum, spin. It's called a spinor field, and alpha is a spinor index. Do not confuse with space-time indices. So what we're going to do, we get the notation right here, is okay, we're going to use let's say mu nu space-time indices go from 0 to 3. We're going to use spinor indices alpha or beta. So I know we've sometimes used alpha and beta to denote space-time indices before. What we're going to do in the next couple of lectures, hang on, we need to distinguish between spinor indices and space-time indices. It just so happens that the number of spinor indices is 4, the same as the dimensions of space-time, but they're actually completely distinct things. There are space-time indices, you go from 0 to 3, and the spinor indices go from 1 to 4. Also beware that psi is not a Lorentz 4 vector, i.e. does not transform like a, so you may say, hey, what do you mean it's not a 4 vector? It's a 4-dimensional column vector. So in a mathematical sense, it's a 4-dimensional vector. But it is not it does not transform like a space-time four vector. If I have a 4 vector in space-time, it has a certain transformation law under a Lorentz transformation. We're going to see how this field transforms under a Lorentz transformation. It does have a transformation law, but it's more complicated than there's a more complicated transformation law that is related to the intrinsic spin of the field. We'll come to that. There's not a Lorentz 4 vector, so be careful. Here you can have two kinds of indices running around. You've got spinor indices and space-time indices. So let me write this here. Spinor indices. Spinor indices. Alpha, beta, going from 1 to 4. Space-time indices. Going from 0 to 3. Completely different kinds of things. Okay, so all that just to tell you what the field is. What about the equation for the field? All right, so we've got so let's write down. So what I'm going to do is write down the Dirac equation. First in the original historical form. I I had thought of not doing this and just writing it down immediately as it's usually used, but occasionally you see it's still written this way. So it's one of these things, you need to be familiar with it. So I'm going to write it down in its original form, and then I'll show you how it's more usually written. And then let's just forget about the historical form. You don't really need to know this, but just for completeness, so it looks like this. This is the Dirac equation as it was originally written. Where note, remember sign is a four-component complex spinor field. Alpha and beta, or we could write it like this: alpha 1, alpha 2, alpha 3 beta. So here I've written it as if it's a vector, but it's really, it's just that it has three components. These are 4x4 Hermitian matrices. Now note, everything here is classical. There are no operators. This is classical. There are no operators. There are no operators. So later, when we do the quantum field theory, the classical Dirac field will become an operator field. Okay, but that's later. The classical Dirac field will be promoted to an operator, just like the Klein-Gordon field is promoted to an operator field. But forget about that for the moment. We're just looking at imagining there's no quantum mechanics, there are no operators here. It's just, these are just C numbers, they're complex valued and they're arranged as a column vector. And the wave equation, so this is, if you like, is equivalent to, this is the wave equation for the Dirac field. The Dirac field has four components. So here you have 4x4 Hermitian matrices, which obey the following relations. The alpha I and j, the anti-commutator is equal to 2ij. So of course you know that the anti-commutator of two matrices is just AB plus BA. We also have the anti-commutator of alpha I with B is 0. And we have beta squared is 1. When we say 1, of course, we really mean the unit matrix, the unit 4x4 matrix. This is the Dirac equation in the original form. I missed anything here. Okay. So let's rewrite this slightly to get the Dirac equation as it's usually written. Is let's multiply each side. Okay, let's multiply each side by beta. If you multiply each side of the Dirac equation by beta, you get the Dirac equation. This is the Dirac equation as you really want to remember. I'm going to rub all this out in a minute because we don't really want this original form. This is how we want the Dirac equation. is written like this. I gamma mu d psi by dx mu minus m psi equals 0. Where the relationship to the other version is that, well, gamma, so sorry, here we have, okay, the gammas here. We've got gamma 0. Remember the space-time indices. Mu is a space-time index. Remember, mu is a space-time index going from 0, 1, 2, 3. Gamma 0 is just beta. Gamma I is beta times alpha I. I is 1, 2, 3. And what you find is that if you look at these commutation relations for the alphas and betas, this can be summarized as follows. The gammas obey the following anti-commutation relation, and they obey the following hermiticity condition, that the Hermitian conjugate of gamma mu is equal to gamma 0, gamma mu, gamma 0. Now you can check that these this here contains the same information as all this here with this translation. The gamma 0 is beta and gamma I is beta alpha I. Okay, so you can start with the original version, just multiply each side by beta, define these things here, and you get this. That's how it happened historically. Now, we actually don't care about the old version. We're not going to be using it. You might see it now and again, but it is rarely used. So what we can say is, never mind about that. What we could have done is I could have just introduced the Dirac equation as follows. I say there is a 4-component spinor field, which I can write as a column vector. Okay, it's a 4-component complex spinor field, and it obeys this wave equation. Where the matrices gamma, they're often called the Dirac gamma matrices. So gamma mu, where mu is a space-time index. There's one gamma matrix for each time and space component, as must be, because here we're taking a derivative with respect to time and with respect to space. We're summing over the space-time index. The gammas, these are 4x4 matrices. 4x4 matrices. And these matrices are defined by these conditions. Any set of matrices which satisfies these conditions is a Dirac matrix. And these conditions don't fix the matrices uniquely. There are different choices of matrices that satisfy these conditions. But those different choices are physically all equivalent. Any set of 4x4 matrices that satisfies these equations, you can show that there is an equivalence transformation. If I have a Dirac equation, let's say I have two sets of gamma matrices that satisfy these conditions. You can perform a transformation on the Dirac field such showing that actually these are just different representations. They're physically equivalent. If you're interested in seeing details like that, you can look at the Appendix A of the book by Mandel and Shaw that goes into some of these details. We're not really going to need these details, but I just thought I'd mention in case you're wondering, hang on, there are different choices of gamma matrices that you can use as is convenient, but they're all physically equivalent as long as you satisfy. So basically, the Dirac, so the simple, 15-second statement, what is the Dirac equation? So the Dirac field is a 4-component complex spinor field. It obeys this wave equation where these are 4x4 matrices that satisfy these conditions. They're the anti-commutation relation and the hermiticity condition. That's all you need to know about the classical, everything you need to know about the classical Dirac field, the Dirac equation is there. Now, something that's useful to know is the gamma matrices. We'll be doing a lot of fiddling around with gamma matrices. So there's something, you want to get used to is what you might call gamma matrix gymnastics. There you go. Gamma matrix gymnastics. Everything you need to know about the gamma matrices comes from these two properties. These define the gamma matrices. So any set of 4x4 matrices that satisfy those conditions are gamma matrices. You can deduce everything. So for instance, from the anti-commutation relation, if you put mu equals mu is 0, you get gamma 0 plus gamma 0 is equal to 2. Okay, if we put mu and mu equals 0. So what does that imply? It implies that gamma 0 squared is equal to 1, or the unit matrix. So that's going to come up a lot. The square of gamma 0 is 1. Similarly, if I put mu equals mu is equal to a spatial index, that anti-commutation relation implies that gamma I squared is minus 1. Minus 1. If I put mu is 0, mu is equal to I, so then the metric here, the component is 0, and so you find that gamma 0, gamma I is minus gamma I, gamma 0. These are useful properties. Remember, you definitely want to remember that gamma 0 squared is 1. That comes up constantly. Another thing that's clear, so from the hermiticity conditions, if I put in, well, what happens when I put mu is 0? Let's look at gamma 0, emission conjugate of gamma 0. Well, it's just gamma 0, gamma 0, gamma 0, and gamma 0 squared is 1. So I get gamma 0. So gamma 0 is emission. What happens to take the emission conjugate of gamma I? I get gamma 0, gamma I, gamma 0. Gamma 0 and gamma I anti-commute. So this is minus gamma I, gamma 0, gamma 0. Gamma 0 squared is 1. So I have minus gamma I. So gamma I is anti-emission. And so on and so forth. So all these properties, gamma 0 squared is 1. It's going to come up constantly. But anyway, anything you need to know about the gamma matrices follows from these defining properties. Okay, something to clarify. We've written the Dirac equation in this form where we have suppressed we have suppressed the spinor indices. I don't know if maybe in these politically correct times you're allowed to use the word suppressed. But anyway, we've suppressed the spinor indices. So when we write I gamma mu, so we're writing down the space-time index. But notice, so what this is I gamma 0 decided by the x0 or t, let's call it x0, plus I gamma 1 decided by the x1, which is just x is the derivative with respect to y. Derivative with respect to z minus m psi is 0. Notice that this here is a 4-component column vector. Okay, the psi here is a 4-component column vector. This here is also a 4-component column vector that contains the derivatives. It's just the derivative of this column vector with respect to x3 or with respect to z. So this is a 4-component column vector that looks like this. So if you imagine, here I've got my 4-component column vector psi. I take the derivative with respect to x3. I just take the derivative of each component. So this is a 4-component column vector containing these 4 derivatives. And gamma 3 here is a 4x4 matrix that is multiplying this column vector. And similarly here you have, this is a column vector which contains the time derivatives of the 4 components of the Dirac field. And gamma 0 is a 4x4 matrix multiplying it. So what you can do, and it might be a good idea if you do this at the beginning, you feel a bit nervous about, hang on, I'm not sure what I'm doing here when I write down this equation, the Dirac equation. What you can do is, if you're in doubt, as it says in a footnote in the book, in case of doubt, the reader should write the indices out explicitly. So what you can do is write the Dirac equation. So with spinor indices, so in other words, without suppressing anybody, without being nasty, let's keep the spinor indices. So what does it look like with the spinor indices? So it's just I have, how should I write this? Maybe I could write it, let me write it like this. Write it like this. So this is just this same equation, but with the spinor indices. So in other words, if you write down, if you multiply out all of these matrices with these column vectors, and then you just look at what, each, this is a 4x4 matrix times a column vector, so the result is a column vector for a column 4 vector. Similarly here, each of these terms is a column 4 vector. So the sum of them is just a column 4 vector equal to 0. So this is equivalent to 4 equations. This is 0, this is 0, each of the components is 0. So what I can do, I can then just write down, essentially here I've got 4 Dirac equations. I've got 4 equations. because alpha goes from 1, 2, 3, and 4. In other words, I've got an equation for E, like this. So notice that here the 4 by 4 matrix multiplies the column vector. So this, or you could simply write it like this. I could just write I gamma mu alpha beta d psi beta with respect to x mu minus m psi alpha is 0. Now notice, of course, we're using the summation convention. Summation over repeated indices. And we're assuming the summation convention. So repeated indices are summed over. So the mu's are summed over. Just as in here, you sum over the mu as a space-time index, goes over 0, 1, 2, 3. Beta here is repeated, but it's a spinor index. It goes from 1 to 4. And so it is, there you go, this is the Dirac equation written with showing the spinor indices. Normally you don't bother, so of course this quantity here, this is just the alpha beta component of, so gamma mu is a 4 by 4 matrix, and this is just the alpha beta component of the 4 by 4 matrix, which you could write like this if you like. So, it becomes a bit unwieldy having all these indices floating around, so people tend to prefer to write it like this, but you might want to just, at least at the beginning, think, hang on, just make sure you know exactly what is being done here. All right, so let me just take just a second to define something and then give you some homework. So there's something called the adjoint field. Adjoint field psi bar, which is defined to be the Hermitian conjugate of psi times gamma 0. Notice that the Hermitian conjugate of the 4 components, so we had psi, with psi 1, psi 2, psi 3, psi 4. The Hermitian conjugate is a row, so psi is a column vector, the complex component, psi dagger is a row vector with the components complex conjugated. Here you have the row vector times a 4 by 4 matrix, so this is a row vector, 4-dimensional row vector. Okay, now it's called the adjoint field, and it satisfies the adjoint Dirac equation, I d psi bar by dx mu gamma mu plus m psi bar equals 0. Now, your first homework problem is to check this. Check, so this is homework. So all you need to do, you just want to start with the Dirac equation and take the Hermitian conjugate. So basically what you would do, let me just tell you what you need to do, is you take the Hermitian conjugate of the Dirac equation, and then you multiply from the left, from the right, by gamma 0. And you should find, so you take the Hermitian conjugate of this, multiply from the right by gamma 0, and you should get this. Go through it, check you understand what the indices are doing. And now finally, let me write down for you the Lagrangian density. The Lagrangian density for the Dirac field can be written like this: psi bar I gamma mu d mu minus m psi. This is the way the book likes to write it. I just like to write out the terms like this. Hang on, sidebar, I, gamma mu, d mu minus n. Let's just write it out as I, sidebar, gamma mu, d mu psi, minus m, sidebar psi. Is that right? I, sidebar, gamma mu, d mu psi, minus m, sidebar. Okay, this is the Lagrangian density for the Dirac field. Now what you do is your homework. So you need to treat, so you have psi alpha, the components of the Dirac field, and you have psi bar alpha, the components of the adjoint field. Treat them as independent fields. And the homework is, show that the Euler-Lagrange equations with this Lagrangian density imply the Dirac equation. The Dirac equation for psi plus the adjoint equation for psi bar. Okay, so homework, keep you going over the break.